Utility pole fires, though not uncommon, affected the low keys, causing power outages for a significant number of homes and businesses. These fires were attributed to a combination of environmental factors that created a conductive pathway on the utility poles. Specifically, a prolonged period of dry weather allowed for the accumulation of salt and sediment in the surfaces of the poles and their associated hardware. This buildup, consisting of conductive materials, acted as a medium for electrical current to flow where it shouldn't normally. The crucial catalyst in this scenario was a light, misting rain. Instead of washing away the accumulated salt and sediment, the light rain moistened the deposits, creating a thin film of water that further enhanced the conductivity of the surface. This allowed electricity to track or flow from the energized power lines through the conductive layer of salt, sediment, and moisture to the wooden cross arms of the poles themselves. Wood, when dry, is a relatively poor conductor of electricity. However, when it becomes damp, its conductivity increases. The tracking of electrical current through this pathway generated heat, eventually leading to the ignition of the wooden components, resulting in utility pole fires. Firefighters responded to numerous calls, all of which were confined to the utility poles. Crews from Keys Energy worked to isolate the affected lines, focusing on de-energizing the circuits around the burning poles to ensure safety and to prevent further damage. Temporary repairs were implemented to restore power to the affected areas as quickly as possible. This often involved patching up damaged crossarms and replacing severely compromised poles. A more permanent solution requires replacing the damaged hardware and thoroughly cleaning the poles to remove the accumulated salt and sediment. The underlying issue of the conductive buildup needs to be addressed to prevent future occurrences. The most effective remedy is a steady, sustained rainfall. This would wash away the accumulated salt and sediment, removing the conductive pathway and preventing the electrical current from tracking to the wooden components. In the absence of sufficient rainfall, alternative measures may be considered. Firstly, regular cleaning of utility poles, which involves physically removing the accumulated salt and sediment from the surfaces of the poles and hardware, can reduce the risk of fires. Secondly, the application of hydrophobic coatings or insulators to the poles and crossarms can prevent moisture from creating a conductive pathway. Thirdly, improving the insulation of the electrical conductors and connections can minimize the potential for current leakage. Fourthly, implementing preventative maintenance programs to identify and address potential issues before they escalate. Fifthly, enhance monitoring of weather conditions and proactively taking measures during periods of dry weather followed by light rain. Sixthly, utilizing materials resistant to fire or being non-conductive for utility poles. Seventhly, increasing the inspection frequency of the poles, especially in areas prone to these weather conditions. Eighthly, the use of surge arresters on the poles. Pole fires can cause significant disruptions to power supply, posing risks to public safety and economic activity. Understanding the underlying causes and implementing appropriate preventative measures is crucial for mitigating the risk of such incidents. The situation highlights the vulnerability of electrical infrastructure to environmental factors and the importance of proactive maintenance and monitoring. While a steady rain is the most immediate solution, a comprehensive approach involving regular cleaning, protective coatings, and improved insulation is necessary to ensure the long-term reliability of the power grid. This involves understanding the properties of the materials involved, such as wood, salt, sediment, and water, and how they interact under different environmental conditions. It also requires knowledge of electrical principles such as conductivity, insulation, and grounding to design and maintain a safe and reliable electrical system. Additionally, it's necessary to consider the economic and environmental impact of different mitigation strategies. For example, the use of certain chemicals for cleaning or coating utility poles may have negative environmental consequences. Therefore, a careful evaluation of the costs and benefits of each approach is essential. Utility poles are typically made of wood, steel, or concrete. Wood poles are the most common due to their low cost and ease of installation. However, they are susceptible to rot, insect damage, and fire. Steel poles are stronger and more durable than wood poles, but they are also more expensive and prone to corrosion. Concrete poles are the most durable, but they are also the heaviest and most difficult to install. The crossarms, which support the electrical conductors, are typically made of wood or fiberglass. Wood crossarms are less expensive, but they are also more susceptible to rot and insect damage. Fiberglass crossarms are more durable and resistant to environmental factors, but they are also more expensive. The electrical conductors are typically made of copper or aluminum. Copper conductors have higher conductivity, but they are also more expensive. Aluminum conductors are lighter and less expensive, but they have lower conductivity. The insulation of the conductors is typically made of rubber, plastic, or porcelain. Rubber and plastic insulation are flexible and easy to install, but they are also susceptible to degradation from sunlight and heat. Porcelain insulation is more durable and resistant to environmental factors, but it is also more brittle and expensive. The grounding system is designed to protect people and equipment from electrical shock. It typically consists of a grounding rod or plate buried in the earth and connected to the electrical system. The grounding system provides a low-resistance path for electrical current to flow back to the source in the event of a fault. Regular inspection and maintenance of utility poles and associated equipment is essential for ensuring the safety and reliability of the electrical system. Inspections should include checking for signs of rot, insect damage, corrosion, and cracks. Maintenance should include replacing damaged poles and crossarms, tightening loose connections, and clearing vegetation that could interfere with the electrical conductors. Power outages can be caused by a variety of factors, including utility pole fires, storms, equipment failures, and animal interference. Power outages can disrupt daily life, causing inconvenience, economic losses, and safety hazards. It is important to be prepared for power outages by having a backup power source, such as a generator or battery, and a supply of food, water, and other essentials. Power companies have developed detailed response plans to address utility pole fires and widespread outages. These plans involve firstly, assessing the extent of the damage and identifying the areas affected. Secondly, mobilizing crews and equipment to the affected areas. Thirdly, isolating the damaged lines to prevent further damage and ensure safety. Fourthly, making temporary repairs to restore power to critical facilities, such as hospitals and emergency services. Fifthly, conducting thorough repairs to replace damaged poles, crossarms, and conductors. Sixthly, implementing preventative measures to reduce the risk of future pole fires. In situations where multiple utility pole fires occur simultaneously, power companies may need to prioritize repairs based on the severity of the damage and the impact on customers. Factors considered in prioritizing repairs include firstly, the number of customers affected. Secondly, the presence of critical facilities in the affected area. Thirdly, the safety of the public and repair crews. Fourthly, the feasibility of making temporary repairs. Effective communication with the public is crucial during power outages. Power companies should provide regular updates on the status of repairs, estimated restoration times, and safety precautions. Customers can also play a role in preventing utility pole fires by reporting any signs of damage or potential hazards to the power company. For example, if you notice a leaning pole, a sagging wire, or a burning smell near a utility pole, you should report it immediately. The National Electrical Code, or NEC, provides guidelines for the safe installation and maintenance of electrical systems. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Electrical contractors and electricians are required to follow the NEC when installing and maintaining electrical systems. This helps to ensure the safety of people and property. Some key NEC requirements related to utility poles include firstly, the minimum clearance between conductors and the ground, buildings, and other objects. Secondly, the proper grounding of utility poles and equipment. Thirdly, the use of approved materials and equipment. Fourthly, the installation of overcurrent protection devices to prevent damage from short circuits and overloads. Fifthly, the regular inspection and maintenance of utility poles and equipment. The specific NEC requirements for utility poles vary depending on the voltage of the electrical system, the location of the poles, and other factors. It is important to consult the NEC and other applicable standards when designing, installing, and maintaining utility pole systems. Additionally, local codes and regulations may impose additional requirements. These should be adhered to as well. Ongoing research and development efforts are focused on improving the safety and reliability of utility pole systems. This includes developing new materials that are more resistant to fire, rot, and insect damage, as well as new technologies for detecting and preventing electrical faults. For example, some companies are developing composite materials for utility poles that are stronger, lighter, and more durable than wood or steel. Others are developing sensors that can detect electrical arcing and other signs of potential problems. These advancements can help to reduce the risk of utility pole fires and other power outages. The overall reliability of an electric grid hinges on careful engineering and maintenance practices that minimize risk. This is due to the complex environmental conditions that the lower keys face, including storms and other sources of damage to electrical grids. This is why planning and action is important.